Hello, this is the first video in Unit 9, Alkyne reactions ready for synthesis. And alkynes are molecules that have a carbon-carbon triple bond. This is a cartoon. I actually have a t-shirt of this cartoon that illustrates that when you look at the hydrocarbons, alkanes, alkenes, which we've seen before, and now alkynes, they're differentiated by the type of carbon-carbon bonds they have. You have single bonds, all single bonds for alkanes. You have at least one double bond, carbon-carbon double bond for alkenes. And here we have a carbon-carbon triple bond. Now, this unit is really the first unit where we're going to have enough reactions to start doing legitimate, full-blown syntheses. Syntheses that have 3, 4, up to 10 reactions that are ordered to go from a starting material, normally a inexpensive starting material, to a molecule of interest, whether it's something that reacts with drugs or enzymes, or maybe a molecule that fluoresces or converts solar energy into electrical energy. You can do a lot of things with, if you know the basic rules of synthesis. But before we do that, I want to start out with the structure and nomenclature of alkynes, both of which are pretty simple, and a lot of this will be review for some of you. Also, we're going to talk about acid-base properties, and then we'll be ready for our list of alkyne reactions and start putting them together in synthesis problems. Okay. Structure. Like I said, an alkyne is a molecule with a triple bond. And let me see what I can draw here. H3, H2, C. Okay. Well, this is a condensed structure, and what's unusual about this structure is that you have these carbons that appear to have no hydrogens on them. So as you're going through your bonding rules, how do we interpret something like this? Well, we're going to add pi bonds to replace the hydrogens that are missing. We have 1, 2, 3, 4, 5 carbons. 1, 2, 3. So that third carbon doesn't have any hydrogens on it. So probably we'll put a triple bond there. That takes us to this fourth carbon. And then the fifth carbon we have right there. You notice that I put dots on all the carbons just to make sure that I'm not missing any carbons. And also, the carbons that are surrounding this triple bond, the 4 atoms around this triple bond, are linear. And we'll see why in just a bit. So this angle is 180 degrees. In terms of hybridization, the way that I teach it is that you count the number of balloons, and the balloons around a carbon represent the areas of electron density. Now, a bond and a lone pair count as an area of electron density, but also double bonds and triple bonds, each of those count as only one area of electron density. So here we have around this carbon 2 balloons. 2 balloons. And that's synonymous with an sp, because we have 2 atomic orbitals mixing to make 2 sp orbitals. You know that atoms that are in the second row have 3 p orbitals. For a lot of them, some of those p orbitals are empty, but they still exist. What that means is that you have 2 unhybridized p orbitals, and the third one was mixed with a s. This also should be synonymous with linear and 180 degrees. The geometry made by the areas of electron density. Okay, let's think about this sp atom. You have a carbon, and I said that you have 2 sp orbitals, because when you mix 2 atomic orbitals, you should get out 2 hybrid orbitals. And when you hold 2 balloons from the tips, for the most part, they're going to be across from each other on average. So these are the sp orbitals. I mentioned that you have two unhybridized p orbitals. Those are going to be, in my drawing, horizontal, and one set of p orbitals vertical. Or not vertical, but towards us and away from us. That represents an sp carbon. Carbon has 4 valence electrons. Okay, 1, 2, and we'll put 1 in each p orbital. So if we really want to make a triple bond, the picture I'm trying to draw in terms of orbitals is this picture here. We'll simplify it, and we'll have the simplest alkyne. So we have a carbon next door, and we have the same set of orbitals. Okay. We're going to hope that we can see what is making these 3 bonds. And I'm missing a p orbital. Okay, it gets a little bit crowded, and we have 4 electrons. And again, with a p orbital, it doesn't matter which lobe you put those electrons in. This. And we have 2 hydrogens. You know where those hydrogens go? They're right here. This is why alkynes are linear, because to have the correct orbital alignment, you're going to form a linear shape between these 4 atoms. And in this case, it's hydrogen, hydrogen, carbon, carbon, hydrogen, carbon, carbon, hydrogen. Hydrogen has 1 electron, valence electron, and that is called an s orbital, right? The 1s orbital. So where is this triple bond? We definitely have a bond between 2 sp orbitals. We have a bond because technically these p orbitals are overlapping. You got to imagine these carbons a little bit closer and the p orbitals a little bit wider. It's just that we normally draw it like this because it gets really hard to see the individual orbitals if they get too close. But we have interactions now between the p orbitals that are aligned. Okay. So that's the orbital picture. All the electrons are there. I think we have a total of 10 valence. 1, then 5, then 9, 10. Okay, 10 electrons. Alright. We know our bond angles, and lastly, before we move on, we know what's making this triple bond. You have a sigma bond between a carbon sp and a carbon sp, and you have 2 pi bonds. The pi bonds are made by, for the vast majority of cases, 2 p orbitals overlapping. So you have Cp, Cp, and another pi bond. We could call this the vertical pi bond, and this one is the one towards us and away from us. And it's also between 2 p orbitals. Let me just get that. Okay. I have a model set here. If you have these types of models, the ones that are called HGS, let me see if I can make this triple bond real quick. I like these models because, well, A, all the carbons are identical. If that carbon is tetrahedral or trigonoplanar, or in this case linear, it doesn't matter which black atom you use, it will still work. So here, I know it's hard to see. Let me just make this triple bond real quick. We have 3 of those curved pieces right there. And then we got to connect them to another sp carbon. But again, the models, it's not necessary to have a piece for sp carbon, a piece for sp2, a piece for sp3. Even the sp3 tetrahedral carbon piece, you can make it, actually you'll use it in this triple bond. And it's not cooperating. Come on. Not as easy, but there. Okay. Then let me put up our hydrogens. My goodness. linear. Okay, linear. Okay, so that's the linear. Actually, the models also can show us pi bonds using those lobes, and I actually want to show you that as well. Okay, so we have p orbitals overlapping, and I'll make one set blue and one set green if I have enough pieces. Give me 1 second. Oh, man. I should have paused the video. Let me just make sure I can do this. Yes, I will pause the video. I'll be right back. Okay, I am back. And so there's, we can see the three bonds of the triple bond. It's linear. It's just that this piece is a little bit tight. But it's definitely linear. Okay. And then for the p orbital visualization, we have this molecule here. Okay. And so we do have to align, right? Align our p orbitals to make sure that they have maximum overlap. So there's one pi bond, blue lobes, and then I didn't have enough green lobes, but if I twist it or rotate it, here's the other pi bond right there. Okay, so again, it's linear. So we can't have something like this. We can't have misalignment. So here, that is misalignment. We don't see they're not lined up, and we have stuff like that. You gotta get these p orbitals to align like this. Okay. Okay. Not the best example in terms of the view. I should have zoomed out a little bit. Anyway, oh my goodness. Those are your models. They mimic the triple bond. Why don't we, I actually do need to talk about bond lengths. So here we have an alkane, an alkene, and we know that alkenes can possibly have cis and trans. Okay. And then we have the alkyne. In terms of bond lengths, it's actually really good to know, because later on we're going to see that it's important to know the bond lengths to fully understand resonance. Okay, because with resonance we have atoms or pairs of atoms that sometimes in some Lewis structures have single bonds, other times they have double bonds, and we've talked about hybrids when we combine two resonance contributors together. Well, when you have hybrids, we don't have a full single bond or a full double bond or a full triple bond. We have in-betweens, and we can see that with bond lengths. Here we have a carbon-carbon single bond, and that's going to be 1.5 angstroms. You know that an angstrom is 10 times 10 to the minus 10 meters. Okay. When we go to a double bond, we actually go to 1.3 angstroms approximately, and then a triple bond is even shorter, 1.2 angstroms. Okay. And you can imagine if you have a resonance hybrid structure where one contributor has a carbon-carbon single bond, and that same carbon-carbon bond is now a double bond in another contributor, you would have an average bond length, and it would be 1.4 angstroms. Okay, and it's still just a good idea to realize the relative size of these bonds in terms of meters or angstroms. Okay. Bond strength, I'm not going to give you any numbers, but this is a stronger bond, right? Triple bonds are stronger than double, and those are stronger than single bonds. Okay, that's all I want to say about that. Nomenclature. Nomenclature, I'm not going to go over the rules. I'm just going to give you some examples, but they're pretty easy. Okay, especially for this video, I'm not going to go through many complicated types of alkynes. And maybe one I want to do is we put a bromine here and triple bond like this. You number from the end closest to triple bond, regardless of where your other substituents are. The only other substituents I would consider in this video are halides and methyl group, alkyl groups. Okay. So if you have those types of substituents, the triple bond wins, and you number from the end closest to triple bond. Now there are other functional groups that have priority over the triple bond, but I'm not going to go through that. And for my class, we're not going to worry about super complicated molecules where we have multiple functional groups. Okay. Again, when you have a halide, or even if you have what do you call it, an alkyl group, I'll put an alkyl group here, like a methyl group, you still number from the end closest to the triple bond. So in this case, we have a bromo at 6, and now I just added a methyl. You alphabetize your substituents: 6 bromo, 5 methyl. You locate where the triple bond is. 3. It's a heptane, but instead of ane, you use ione, heptine, just like porcupine. That should be the name there. Along with alkenes, you can't get distracted if it appears that your triple bond is not part of the parent chain. It actually has to be part of the parent chain. So for instance, if I have something like this, okay, and the longest continuous carbon chain is 1, 2, 3, 4, 5, 6, 7, 8, but you have to include both carbons of the triple bond. So we can't count that way. We have to count from here, and we have 1, 2, 3, let's go to the left, 4, 5, 6, 7. So it's not actually 8. The longest continuous carbon chain that includes the carbons, both carbons of the alkyne, is 7. And this is our substituent. It's a propyl group, and it's on carbon 3. 3 propyl. I did another 7 carbon chain. Locate the triple bond 1. Again, we have a heptine. Okay. It's going to be rare that we're going to see a triple bond within a ring, within a cyclic system, because 4 atoms are linear. Like 4 atoms are linear. So we need a lot of more atoms to try to complete the cycle. Okay, when you have atoms that are linear, right? That doesn't help us swing around to connect the two ends. So typically, molecules that have carbon-carbon triple bonds in a ring are fairly big because you need enough atoms to swing back around to hit the other end. One example is this. 1, 2, 3. When you try to make this model, okay, the model is going to try to be linear, but the shape is going to constrain or put stress on the bonds, and they're going to have to be a little bit bent. Okay. And I'm drawing this. Okay, so that's a triple bond. Why don't we put a substituent? Let's put a, well, let's try isopropyl. Right here. Okay. You have to include both carbons of the triple bond, and those carbons have to be 1 and 2 when you have a ring. 1, 2, 3, 4, 5. If you go counterclockwise, 1, 2, 3, 4, 5, 6, 7. So we're going to number it this way. Okay, it's a 9 carbon ring. When you have a multiple bond, like a double bond or a triple bond within the ring, that multiple bond is automatically carbon number 1 if you have just one of them, one multiple bond. So there's no need to number where the triple bond is, but we do need to number where the isopropyl group is, and isopropyl is an acceptable name for that group. It's not strictly IUPAC, right? IUPAC is what is this? 1-methyl ethyl. Remember how to do that? 1-methyl ethyl. I won't go over that here. I'll use the more common name isopropyl. You don't have to number where the triple bond is, and it's a cyclo, and it's 9. No, not nonane, but nonine. Okay. For the last 8 minutes, I want to go over, and that's it for nomenclature. I want to go over some acid-base chemistry. That's going to be really important when we start using these alkynes to build bigger molecules. Because one way to build a molecule, a bigger alkyne, is to deprotonate an existing alkyne and just add nucleophiles to the end. Or not nucleophiles, add electrophiles to the end. Acid base. It will become apparent once we go over some acid base properties. If you recall your pKa table, something like methane, and we have here Ethyne and Ethyne, the triple bond. Due to hybridization, the alkyne is actually the most acidic. It's still not very acidic relative to other molecules. Okay, 55 to 60. This one, I'd say normally 45, and this one is 25. So what are we doing? We're losing this proton that I'm putting in the square. Okay, any one of those protons. So let's deprotonate this alkyne. This is Ethyne. I should have mentioned this. So the common name is, not common, the IUPAC name is Ethyne. But this has a common name that people use a lot. Acetylene. Don't ask me why there's an E. Okay. Acetylene, you've heard of acetylene torch. Okay. So that's the common name. IUPAC obviously is Ethyne. Okay, not ethane. Let me draw you an acid-base reaction, and we're going to go back and review how to figure out the products, how to figure out the equilibrium arrow, okay. Remember these types of problems? Given an acid and a base, can you figure out what the conjugate acid and conjugate base are and fill in the equilibrium arrow properly? You can even do mechanisms. So here's the base. There are 2 lone pairs. You got to be very careful. Make sure your grader sees that. When you draw 1 lone pair to use as part of your mechanism arrow, you have to draw all the lone pairs. So there's your proton. This is definitely the base, because we're not going to make this an acid and have it lose another proton. That would make this nitrogen -2. There is no such thing as an atom that's more than -1 or +1. There's no -2 or +2 atom in general. So we could definitely draw our products. CH3, C. I'm drawing the sort of the condensed Lewis structure here, and we have a lone pair. Okay. Plus NH3. This molecule is going to be super important when we talk about other reactions in the unit and start doing synthesis. You could call this an alkyne anion, or I think alkenyl anion. Either one. Okay. Either one. How do we do the equilibrium arrow? You look on each side for the acid and you compare pKa's. pKa equals 25. For ammonia, pKa equals 36. Equilibrium favors the weaker acid. That's weaker acid. Okay. So to deprotonate this alkyne, okay, where the triple bond is at the end and we have this hydrogen, we need a pretty strong base. How do I know this is a strong base? Because it resulted in a pretty weak conjugate acid. It's even weaker than our alkyne. Contrast to a base that most people would first try, sodium hydroxide. When you have sodium hydroxide, NaOH, you know that the ionic species will separate and we have O-. Same deal. Okay. Go ahead and figure out the products, the mechanism, and the equilibrium, and you can double check it after you unpause the video. So go ahead and pause the video. Okay, I'll draw the mechanism first. Again, same deal. Grab the terminal proton, push the 2 electrons onto the carbon, and we have this. Same alkyne anion, but now we have a different conjugate acid, H2O. This alkyne has a pKa of 25. Water has a pKa of around 16, or my chart has 15.5. Equilibrium favors the weaker acid. The larger arrow goes to the left. What this means is that, or my conclusion is that, OH is not a strong enough base to what? To fully deprotonate the alkyne. And specifically, it's a terminal alkyne, where the triple bond is at the end. When we have to deprotonate an alkyne, or even when we have to do reactions that use a base, we'll see that we can do elimination to make an alkyne in the next video. You want to use NH2-, but it's going to be seen most likely in this chemical storeroom or on an exam as NaNH2. It's called sodium amide. Okay. Don't worry why it's called an amide. I'm not 100% sure why. Because amides usually have a, well, for me, they have a carbon-oxygen double bond. But you want to make sure that you understand that this separates into Na plus NH2-. And you notice that this is the species we use in the mechanism, because you have to show the lone pairs and show that it's anionic. Okay. Our next video, we are going to start doing reactions, and I'll show you how to string a couple of reactions to do a synthesis, in particular the synthesis where we go from alkane to alkene alkyne. So that's going to be pretty exciting.